Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to be continuing our exploration of thermodynamics by looking at how internal energy changes within a system. First, we're going to focus on how energy is transferred as work, especially in gas-phase systems where volume and pressure changes are key. After that, we're going to shift to the concept of heat and discuss how thermal energy is transferred. Here, we're going to cover heat capacity, specific heat, and we'll wrap up with calorimetry, which is a powerful technique for experimentally measuring heat changes during physical and chemical processes. To start, let's do a quick review on the two essential equations we saw in our previous lecture. We have the first law of thermodynamics. This tells us that the change in a system's internal energy, delta U, is going to be equal to the sum of the heat added to the system and the work done on the system. So in mathematical form, we say that delta U is equal to Q plus W. This equation is fundamental because it reminds us that energy cannot be created or destroyed. It can only move or change forms. Any change in the internal energy of a system has to be accounted for by energy entering or leaving as heat or work. Now, let's zoom in on the work term in this equation. In physics, work is defined as a force acting over a distance. In thermochemistry, we're going to apply this concept to chemical systems, especially gases. For example, think about a gas inside a cylinder with a movable piston. If the gas expands, it's going to push the piston upward, and it's going to apply a force over a distance. That's mechanical work, and in basic terms, again, we can describe it as force times distance. But in chemistry, we typically deal with a very specific form of mechanical work called pressure volume work, or PV work. This occurs when a gas expands or compresses while pushing against an external pressure. By substituting pressure and volume into our general work formula, we get that work is equal to minus pressure delta V. P here, this represents external pressure that's applied to the system. And delta V is the change in the system's volume. It's going to be final volume minus initial volume. Then this negative sign that we have out front, this is very important. It reflects the chemistry sign convention, which always views things from the perspective of the system. So if the gas expands, it's doing work on the surroundings, meaning it's losing energy, so work is going to be negative. On the other hand, if the gas is compressed, then the surroundings are doing work on the system. They're adding energy to it, so W, work, is going to be positive. Again, to visualize this, imagine a piston. If a gas expands, it's going to push this piston upward. So the volume is going to increase. That means delta V is going to be positive. If delta V is positive, then that means work is going to be negative. And that means energy is leaving the system. But if the gas is compressed and the piston moves downward, then the volume decreases. So delta V is going to be negative. If delta V is negative and we have these two negatives that multiply together, that means work is going to be positive. And that tells us that energy is entering the system. This concept is especially relevant because many chemical reactions that we run in the lab happen to be in open containers, beakers, flasks, and so on. And that means they're going to be carried out under constant pressure conditions. And in those cases, the work being done is always pressure volume work. And we're going to use this equation, work is equal to negative P delta V, to understand the work that is being done onto the system or by the system. Finally, one last important detail. In many problems, we're going to be asked to convert PV work into SI units like joules. Since pressure is usually given in atmospheres and volume is usually given in liters, we need to know that 1 liter times atmosphere is equal to 101.3 joules. We're going to see this conversion factor used often in practice problems, so be sure to keep it in mind. Now let's go ahead and apply what we just learned to a couple of concept check problems. This first one says, what is the work done if a piston decreases from 4 liters to 2 liters with 2 atmosphere of pressure? And is it done on the system or the surroundings? Convert into joules. Let's work through this step by step. We're given that the gas volume decreases from 4 liters to 2 liters. So we know that this is going to be a compression. The system is being compressed by the surroundings, which means that work is being done on the system. And we expect our answer for work to be positive. Since this is a direct volume change, we can use the formula for pressure volume work. Work is equal to negative P delta V. We're given the pressure, it's 2 atmosphere, and we're given enough information to calculate delta V. Delta V is final volume minus initial volume, so 2 liters minus 4 liters, and this gives us negative 2 liters. Now we can take all our values and plug them into our equation. Work is equal to negative 2 atmosphere multiplied by negative 2 liters. This gives us a positive value, 4 liters times atmosphere. Now, this problem specifically asks us to convert into joules. So we're going to need our conversion factor to do that. 1 liter times atmosphere is equal to 101.3 joules. So we take our final calculation here, 4 liters times atmosphere, and we know for 1 liter times atmosphere, that's going to be 101.3 joules. So we use this conversion to get our final answer in joules. Notice that these units cancel out. We carry out the calculation and we get 405.2 joules. So this is the work done if a piston decreases from 4 liters to 2 liters with 2 atmospheres of pressure. And we figured out that this is going to be work done on the system. Let's move on to the second problem. The second problem says, what is work for the chemical reaction below at 300 Kelvin? And is it done on the system or the surroundings? This chemical reaction tells us that we have 2 moles of hydrogen gas. It reacts with 1 mole of oxygen gas to give us 2 moles of liquid water. For this problem, we're not given a change in volume directly. Instead, we're dealing with a change in the number of gas molecules during a reaction. When this is the case, we use a version of the work equation that's based on the ideal gas law, and we saw this in the previous lecture. That equation is that work is equal to negative delta Ng multiplied by RT. Let's break this down. Delta Ng is going to be the change in the number of moles of gas, and it's calculated as moles of gaseous products minus the moles of gaseous reactants. Then we have R. R is the gas constant. We've seen this previously in our gas unit, but here, since we want our answer in joules, we're going to use a slightly different version. R is equal to 8.314 joules per mole times Kelvin. And finally, T is temperature, and we're told that's equal to 300 Kelvin. The only thing we need to figure out before we start plugging things in is delta Ng. Let's compute that. This is going to be the moles of gaseous products minus the moles of gaseous reactants. Looking at our products, we have 2 moles of water, but it's liquid, so it doesn't count towards gas moles. So the moles of gaseous products is 0. This is going to be 0 minus the moles of gaseous reactants. We have in our reactants 2 moles of hydrogen gas and 1 mole of oxygen gas for a total of 3 moles of gas. So delta Ng is equal to 0 minus 3, which is negative 3. Now we can start to plug everything into our equation. Work is equal to negative minus 3 multiplied, and this is minus 3 moles, multiplied by R, which is 8.314 joules divided by mole times Kelvin, and that's multiplied by temperature, which is 300 Kelvin. Notice that moles cancel out, Kelvin cancels out, and the unit we're left with is joules, which is exactly what we want when we're calculating work. Plug this into a calculator and you're going to get 7,482.6 joules, and that's equal to 7.4826 kilojoules. So the system gains 7,482.6 joules of energy as work. And because this work is positive, that tells us that the surroundings have compressed the system. So it has done 7,482.6 joules of work that is done on the system. Now that we've seen how energy can be transferred as work, let's shift our focus to heat, which is the other major way that energy is transferred in thermodynamic systems. While the terms heat and temperature are often used interchangeably in everyday language, they mean very different things in science. Temperature is a measure of the average kinetic energy of the particles in a substance, so how fast they're moving. Heat, on the other hand, is the energy that flows between objects because of a temperature difference. So when something feels warm or cold to the touch, it's because heat is flowing into or out of your body, and not because your skin is measuring temperature directly. Now, although heat and temperature are not the same thing, we can still use temperature changes to calculate the amount of heat transferred. And that's where heat capacity comes in. The quantity that ties heat and temperature together is called heat capacity. Heat capacity is defined as the amount of heat required to raise the temperature of a given amount of a substance by 1 degree Celsius. Then there's specific heat capacity. This is defined as the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Finally, if we're working in moles instead of grams, we use molar heat capacity, and this is the amount of heat needed to raise the temperature of 1 mole of a substance by 1 degree Celsius. This gives us 2 very important equations for calculating heat. If we're working with mass in grams, we use this first equation. Q is equal to mc delta T. M is the mass in grams, C is going to be the specific heat capacity, and delta T is the change in temperature. C is going to have units of either joules per gram times Celsius or joules per gram times Kelvin. If we're working with the number of moles, we use this other equation. Q is equal to N Cm delta T. N is the number of moles, Cm is the molar heat capacity, and delta T is the change in temperature. For the molar heat capacity, it's going to have units of either joules per mole times Celsius or joules per mole times Kelvin. Regardless of whether you use Celsius or Kelvin, or whether you convert between these values, the value of delta T stays the same because it's a difference between two temperatures and both scales increase at the same rate. What that means is that a 1 degree Celsius change is equal to a 1 Kelvin change. So if you have your initial temperature to be equal to 0 degrees Celsius and your final temperature is equal to 10 degrees Celsius, delta T is going to be 10 minus 0, and that's equal to 10. If you convert these temperatures into Kelvin, it's going to be 273 Kelvin for the initial temperature and 283 Kelvin for the final temperature. And if you went ahead and calculated delta T, 283 minus 273, notice you get the same delta T value. So the important point here that I was trying to make is that regardless of whether you use degrees Celsius or Kelvin, the value of delta T stays the same because it's a difference between two temperatures and both scales increase at the same rate. Now that we know how to calculate heat using temperature change, let's take a moment to think about what determines how much heat a substance can actually absorb. In other words, what factors influence the heat capacity of a material? One important thing to remember is that heat capacity isn't the same for every substance. It varies depending on both the nature of the substance itself and how much of it you have. So as a general rule, heat capacity tends to increase with three things: the size of the molecule, the number of moles or mass present, and the strength of the substance's intermolecular forces. Large or more complex molecules have more ways to store energy through vibrations, rotations, and movements of their atoms, so they can absorb more energy before their temperature starts to rise. Similarly, substances with strong intermolecular forces like hydrogen bonds, they resist temperature change because it takes more energy to overcome those attractions. A perfect example is water, H2O. Thanks to hydrogen bonding, water has a high specific heat capacity of 4.18 joules per gram times Celsius, which means it can absorb a lot of heat without a big temperature change. That's why water is so effective at regulating temperature in both nature and in our own bodies. Compare that to metals like copper or lead. Their specific heat capacities are much lower, around 0.3 to 0.4 joules per gram times Celsius. And that means they heat up very quickly when they're exposed to energy. And you've probably noticed this when you're touching a metal object that's been sitting in the sun. It gets hot fast. Understanding these differences in heat capacity becomes especially important when two substances come into thermal contact and then exchange heat. For example, when you drop a hot piece of metal into a cup of cool water. In this kind of situation, energy doesn't just sit still, it moves. Heat will naturally flow from hotter object to the cooler one until both substances reach the same final temperature, and this is a state known as thermal equilibrium. And as long as no heat is lost to the surroundings, the amount of energy lost by the hotter object will be gained by the cooler one. And that gives us the relationship that Q1 is equal to Q2. Now, we're not saying that the temperature changes are equal. What we're saying is that the amount of energy transferred is equal in magnitude. And to calculate this, we can apply the heat equation to each substance. So the heat equation for substance 1 is equal to the heat equation of substance 2 because Q1 is equal to Q2. This version assumes we're using mass-based specific heat, but if you're working with moles and you're using molar heat capacity instead, the structure of the equation stays exactly the same. So either form is completely valid. Just make sure that your units match your equation. If your heat capacity is given per gram, use mass. If it's given per mole, use the number of moles. And always double check that the units for temperature change are consistent with the units in your heat capacity. This kind of setup shows up often in calorimetry problems, and it's a powerful tool for figuring out unknowns like final temperature, specific heat, or the amount of energy transferred between substances. Let's tackle some problems now. This first one says, for the same mass of water and copper, what is the change in temperature for water if the same amount of heat added to copper increased its temperature by 10 degrees Celsius? And here we're given the specific heat capacity for both water and copper. Since the same amount of heat is added to both, we can set their heat expressions equal to each other. So we can write that the mass of water multiplied by the specific heat capacity of water multiplied by the temperature change for water is equal to the mass of copper multiplied by the heat capacity of copper multiplied by the temperature change for copper. In the question stem, we're told that the masses are the same. So the mass of water is equal to the mass of copper. So we can go ahead and get rid of these terms. This simplifies our expression. Ultimately, our goal is to solve for the temperature change for water. So we're going to isolate that value. We're going to isolate that variable. And we can do that by dividing both sides by the specific heat capacity of water. So we get that the change in temperature for water is equal to the specific heat capacity for copper multiplied by the temperature change for copper divided by the temperature change of water. We actually have all of these values. The specific heat capacity of copper is 0.4 joules per gram times Celsius, and delta T for copper is going to be equal to 10 degrees Celsius. This is divided by the specific heat capacity for water, which is 4 joules per gram times Celsius. So notice that the units for specific heat capacity cancel out, and the only unit we're left with is degrees Celsius, which is exactly what we want when we're calculating temperature difference. If we plug this into a calculator, we're going to get 1 degree Celsius. So water's temperature only increases by 1 degree Celsius, while copper increased by 10. Why? Well, this is because water's specific heat capacity is much higher. It resists temperature change more than copper. This reinforces the inverse relationship between specific heat and temperature change. The higher the specific heat, the smaller the delta T for the same amount of heat. And we're going to carry this idea into the second problem. The second problem says, consider the specific heats below. If the same amount of heat is added to identical masses of each of these substances, which substance attains the highest temperature change? So here we apply the heat equation again, Q equals mc delta T. And we recognize from the question stem that Q and M are the same for each sample. So we're really just comparing temperature and specific heat capacity, and these variables are inversely related. That means that the smaller the specific heat capacity, the greater the temperature change. All we need to do is look for the substance with the lowest specific heat value. It's going to attain the highest temperature change. And looking at these values, the substance that has the lowest specific heat value is lead at 0.159 joules per gram times Celsius. So it's going to experience the largest delta T under the same heat input. So far, we've learned how to calculate heat using temperature changes and specific heat. But how do we actually measure heat in a lab setting? That's where calorimetry comes in. Calorimetry is the technique we use to measure the heat involved in a chemical reaction or physical process. And the basic idea is simple. If you can track the temperature change of a system and you know its mass and heat capacity, you can calculate the heat that was transferred during the process. Let's start with the most common type of setup, the constant pressure calorimeter, also known as a coffee cup calorimeter. This is typically just a pair of nested styrofoam cups with a lid, a thermometer, and a stirrer. You fill it with a liquid, usually water or an aqueous solution, and you carry out the reaction right in that solution. Since the system is open to the atmosphere, the pressure remains constant throughout. Now, here's the key thermodynamic relationships for constant pressure calorimetry. We know from earlier that the change in internal energy is equal to heat plus work. And for pressure volume work, we saw that work is equal to negative P delta V. We can take this relationship for work and substitute it back into our equation for change in internal energy. And we get that the change in internal energy is equal to Q minus P delta V. Here specifically, we want to note that heat is at constant pressure. So we're going to add a little P to denote that. If we rearrange this, we can isolate the heat at constant pressure. That gives us that the heat at constant pressure is equal to the change in internal energy plus P delta V. This expression is actually the definition of enthalpy, delta H. So when we measure heat in a constant pressure calorimeter, we're directly measuring the enthalpy change for the process. So delta H is equal to QP. That's incredibly useful because many thermodynamic data tables, like heats of reaction or dissolution, are reported in terms of delta H, not delta U. Now let's talk about what this value tells us. Depending on the sign of delta H, we can tell if a reaction or process is exothermic or endothermic. In an exothermic reaction, the system releases energy to the surroundings. This means that delta H is going to be negative, and we're going to observe an increase in temperature of the solution in the calorimeter. The system is losing energy, and the surroundings are gaining it. In contrast, an endothermic reaction absorbs energy from the surroundings. So delta H is going to be positive, and the solution's temperature will drop as energy flows into the system. We can visualize this with energy diagrams. In an exothermic diagram, the products have lower energy than the reactants. So the products have lower energy than the reactants. Heat is released, and that's represented by a negative delta H. In an endothermic diagram, the products are higher in energy than the reactants. So delta H is positive. Energy had to be absorbed to make that happen. Now, both types of reactions, they have this activation energy barrier that has to be overcome. That's the hill in the diagram. But the difference between the reactant and product energy levels is what tells us whether heat is released or absorbed overall. So just to recap, constant pressure calorimetry measures Q at constant pressure, which equals enthalpy, delta H. And by observing the energy of the products compared to the reactants, we can determine whether the process is exothermic or endothermic. Now that we've covered how heat is measured at constant pressure, let's shift to a different type of calorimetry, one that operates under constant volume conditions. This setup is called a bomb calorimeter, and it allows us to measure the internal energy change of a reaction. A bomb calorimeter is designed so that the reaction takes place in a sealed rigid container, often made of strong material, known as the bomb. Inside the bomb, we place a known mass of a sample, typically something that combusts. The bomb is then filled with pure oxygen and tightly sealed to ensure that the reaction will occur in a fixed volume environment. This sealed bomb is then submerged in a known amount of water, and everything is enclosed within an insulated calorimeter vessel. To start the reaction, we use an ignition wire or fuse connected to an electric current. Once the sample combusts, the heat it releases is absorbed by both the water surrounding the bomb and the metal container itself. Importantly, the entire system is stirred continuously, and that ensures that the temperature remains uniform throughout the water bath so that the thermometer gives an accurate reading. Now, here's where the thermodynamics comes in. Because the volume is fixed, no pressure volume work is done. That's because when volume is constant, delta V is equal to 0. And if that's equal to 0, then work is also equal to 0. Then from our first law of thermodynamics, delta U is equal to Q plus W. If we just said that work is equal to 0, then what we're left with is that the change in internal energy is equal to heat, specifically heat that is released or absorbed under constant volume conditions. So in a bomb calorimeter, the heat released or absorbed equals the change in internal energy, not the enthalpy change. I want this to be a key difference that you understand from the coffee cup calorimeter. The coffee cup calorimeter measured delta H under constant pressure. The bomb calorimeter measures delta U under constant volume conditions. Now let's talk about how to calculate the heat. The system is the chemical reaction inside the bomb, and then the surroundings are going to be the water and the calorimeter container. So if the system releases energy, that energy is absorbed by the surroundings. So we can write the following relationship. The heat of the system is equal to the negative heat of the surroundings. This demonstrates this exchange of energy that happens. But in our calculations here, we're just going to focus on magnitude only, so don't worry about the sign. This gives us that Q system is equal to Q surrounding, and our system is just going to be the heat for the water plus the heat of the calorimeter, Q water plus Q calorimeter. We can expand the definitions of both of these from our equation that we saw earlier. Q is equal to MC delta T. So for Q water, we can write MC delta T, where M is the mass of the water, C is the specific heat capacity of water, and delta T is the change in temperature. And then we can do the same thing with the calorimeter. It's just going to be the specific heat capacity of the calorimeter. In other words, the metal that the calorimeter is made up of, multiplied by delta T. So we can use this to calculate the total heat And this is what's used to determine the delta U, the change in internal energy for the reaction. And this is because in a bomb calorimeter, delta U is equal to QV. Now let's tackle some problems together to really understand how we can use this expression. This first problem says a scientist explodes 10 gummy bears in a bomb calorimeter. The temperature rise for 2,500 grams of water is 20 degrees Celsius. The bomb calorimeter housing has a heat capacity of 2,500 joules per degree Celsius. How much energy is in one gummy bear? And here we're given the specific heat capacity of water. We're being asked to find the energy released by one gummy bear. So we'll first calculate the total heat released by the reaction, and then we're going to divide by 10 since 10 gummy bears were combusted. In a bomb calorimeter, we can calculate the total heat released by using this equation. Q is equal to MC delta T plus C of the calorimeter delta T. And again, I'll go over what each of these variables are. M is going to be the mass of the water. C right here is going to be the specific heat capacity of water. Delta T is the observed temperature change. And then C cal is the heat capacity of the calorimeter. And we're given all of this information. We're told that the mass of water is 2,500 grams. We're told that the specific heat capacity of water is 4 joules per gram times Celsius. And we're told that the temperature change is 20 degrees Celsius. In addition, we're given the heat capacity of the calorimeter. That's 2,500 joules per Celsius. And again, temperature change is 20 degrees Celsius. So we've plugged in all of these values that we were given, and we can calculate this, and it will give us 250,000 joules. In other words, 250 kilojoules. This is the energy that's released by all 10 gummy bears. But this problem wants us to figure out the energy released by just one gummy bear. So we have to take this value and we have to divide it by 10. This gives us 25 kilojoules. So this is the energy released by a single gummy bear. The second problem says, which of the following statements about calorimeter experiments is true? Let's go through each option and talk about it. A says water is often used to measure the temperature change because it has a small heat capacity. That's false. Water is used because it has a high heat capacity. It can absorb a lot of heat without a large temperature change, which makes it a reliable medium for tracking thermal energy. So A is not a true statement. B says bomb calorimeters provide a measure of enthalpy by measuring heat at a constant pressure. This is also false. Bomb calorimeters operate at constant volume, so they measure delta U, not delta H. C says the water in a bomb calorimeter must be constantly stirred. That's true. Stirring ensures that the temperature remains uniform throughout the water bath so that delta T is measured accurately. Without stirring, you might get a misleading reading from a localized hot or cold spot. C is in fact the correct answer for this problem, but we're still going to read D. D says calorimeters are sufficiently insulated that the heat change calculated from difference in temperature is completely accurate. This is an overstatement. While calorimeters are designed to be well insulated, they're not perfectly insulated. That's why we include the heat capacity of the calorimeter itself in our calculations, because some energy will inevitably go into heating the container. So the correct answer here is going to be C. Now, we've discussed a lot in this lecture, so I just want to take a moment to summarize some of the key ideas we've covered so far about energy, work, heat, and how they relate to chemical systems. At the center of all of this is the first law of thermodynamics, which states that energy cannot be created or destroyed. It can only be transferred or transformed. So, in other words, the total energy of the universe remains constant. If energy is gained by the system, it has to be lost by the surroundings and vice versa, and this is often expressed in this manner. Then we also introduce one of the most important equations in thermodynamics, which tells us that the change in internal energy of the system is the sum of the heat added to the system, Q, and the work done on the system, W. We learned how to calculate heat using the equation Q equals mc delta T, where m is the mass, C is the specific heat capacity, and delta T is the change in temperature. We also saw how to calculate work, specifically pressure volume work. Work is equal to negative P delta V. Together, these equations allow us to quantify how a system's internal energy changes during a physical or chemical process. We then connected internal energy to a new concept, enthalpy, which is represented as delta H. The relationship is given by this equation. Delta H, the change in enthalpy, is equal to the change in internal energy plus P delta V. This shows that enthalpy captures not only the internal energy change, but also any work done by or against external pressure during a volume change. Now let's relate all of this back to the two types of calorimetry we explored. In a closed system where volume is constant, like in a bomb calorimeter, no pressure volume work occurs because delta V is equal to 0. And this simplifies the first law, and it gives us that delta U is equal to QV. So in a bomb calorimeter, the heat measured corresponds directly to the system's internal energy change. And to calculate this heat, we add together the energy that's absorbed by the water and the calorimeter container, and that's where we get this equation. Here, Ccal is the heat capacity of the calorimeter, and it's included because some of the heat released by the reaction ends up warming the metal container as well. On the other hand, in an open system where pressure is constant, like in a coffee cup calorimeter, we measure the heat associated with the enthalpy change. So in this case, delta H is equal to QP. Any volume changes and pressure volume work that occur are inherently included in the value of enthalpy, in the value of delta H. So the heat measured at constant pressure tells us directly how the enthalpy of the system has changed. And with that, we've completed this lecture. I hope that it has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.